right, guys, here I'm going to be talking to you about reactions of alcohols. So this is section 9.6 through 9.10 in your book here. So first we're going to start with how alcohols react with strong bases. We've done this in class previously. Alcohols react with strong bases to yield alkoxides. So strong bases, again, have to be some kinds of particular bases. Sodium hydroxide is the one that you guys know of and you usually tell me is a strong base, and it is for the most part. Not strong enough to do the reaction that I'm about to show you. You need a much stronger base in order to react with an alcohol to yield an alkoxide. That strong base we're going to use is sodium hydride. Sodium hydride is an ionic compound. When it breaks into its ions, you have the sodium ion and the hydride ion. Hydride ion is the very, very strong base. Remember, sodium ion usually just kind of floats away, doesn't really participate in the course of the reaction, so we don't really have to worry about the sodium ion. But the hydride ion is going to be the strong base. Remember, bases deprotonate acids. So let's take a look and see what happens when we take this molecule here. This is 1, 2, 3. This is 1 propanol. You have to tell me that it's a carbon number 1. It's an alcohol, so the ending gets changed. And there's 3 carbons, all single bonds. So 1 propanol. We're going to react 1 propanol with sodium hydride. I'm going to draw those 2 electrons on the hydride, giving it its negative charge so that we can use them in this upcoming mechanism. So what happens here is, hold on, let me get myself a bond. This is going to make this a little bit better here. What happens here is the hydride deprotonates the alcohol. The electrons that were in the oxygen-hydrogen bond then get localized on the oxygen atom. So the products of the reaction are 1, 2, 3 carbons and an O-. That sodium ion kind of hangs out as the counter ion to that alkoxide, and hydrogen gas bubbles out of the solution. This is propoxide. It is the alkoxide of 1 propanol. It is its conjugate base. Remember, conjugate bases of an acid is with the proton removed. Removal of the proton makes it into the negatively charged propoxide. That is an alkoxide. So let's do one more just so that we really have this clear. Let's take this alcohol. This is T-butanol. If we were naming it sort of a common way, if we weren't naming it common, then it would be 2-methyl 2-propanol. So we have a methyl group here at carbon number 2. We also have the alcohol group here at carbon number 2. So 2-methyl, and then this 2 is telling us that the propanol, the alcohol, is at carbon number 2. There are 3 carbons in the longest chain, so it gets prop. We're going to react that in the presence of strong base, sodium hydride. Just so you know, that's a plus sign there. Okay. Once again, the reaction that occurs is that the hydride deprotonates the alcohol, pulls the proton off. The electrons that were in that bond swing over onto the oxygen, turning it into the O-, the alkoxide. And now it has 6 electrons. Sodium ion, hydride, that goes away. This whole thing is sodium T-butoxide. This part of the molecule here is just T-butoxide. It is an alkoxide. So, what are they good for? Why do we care about having alkoxides? Alkoxides are good nucleophiles. They react with alkyl halides to yield ethers. So, if we had an alkoxide, We'll do this propoxide again. That's 2 separate electrons there. Let's react it with 1 bromobutane. And we'll do this reaction in DMSO. The alkoxide then is a good nucleophile. It's negatively charged. We know that negatively charged nucleophiles are good nucleophiles. This alkyl halide is primary, and the solvent tells us that this reaction is going to occur via an SN2 reaction. Primary cannot go via SN1. It must go SN2. Aprotic solvent also tells us that it's going to go SN2. So just like every other nucleophile electrophile reaction, the nucleophile comes in from the back side and pushes the leaving group away. Be careful here now that we're having larger molecules. The alkyl halide here has 4 carbons in it in the chain, and our alkoxide has 3 carbons in the chain. So don't lose your carbon atoms is basically what I'm saying. So carbon number, I'm going to draw it up here, 4, 3, 2, 1. That's from our alkyl halide. Now we're going to make a bond from carbon 1 to the oxygen. Then from the oxygen, it's going to be bonded to carbon 1, 2, and 3 from the alkoxide. So let me see here. This part here, oh my goodness, why did it disappear? This part here is from the alkyl halide. Let's make this look better. Sorry, I'm having some technology issues. You know, life can never be simple. 1, 2, 3. 1, 2, 3. This part here is from the alkoxide. The name of this molecule, because now we care about nomenclature of alcohols and ethers, that's what this chapter is all about, would be propyl butyl ether, if we were naming it sort of more commonly. If we were naming it more systemically, it would be 1-propoxy butane. We're naming the shorter chain as a substituent off of the longer chain. So off of carbon number 1, we have this propoxy group, and off of the butane. Let's do another one of these. Let's take again our propoxide nucleophile, but now instead let's react it with this alkyl halide, and we're going to do it in the presence of propanol. So hopefully you can kind of see why I'm trying to do this kind of a reaction. If we analyze our nucleophile and our electrophile, you can see our electrophile here is tertiary. Tertiary electrophiles cannot undergo the SN2 reaction. There is too much steric bulk in the transition state. There's no way for the nucleophile to come in 180 degrees from the bromine, from the leaving group. So this reaction, and it's in a protic solvent, is going to occur under SN1 mechanism. So in the SN1 mechanism, what happens first? The leaving group leaves, and you form the carbocation. Now that we form the carbocation is going to react with the nucleophile. So here's our electrophile already. We're going to form a it doesn't like when I do that. We're going to form a bond to the oxygen, and then the oxygen has 1, 2, 3 carbons coming off of it. So you can see here is the alkoxide. And here was the alkyl halide. All right, so now we have to name it. So again, we're going to name the shorter chain as a substituent off of the longer chain. This is 1, 2, 3, 4. So this is going to be, so propoxide, so 2-methyl, 2-propoxy, butane. So alcohols react with strong bases to give you alkoxides, and alkoxides are good nucleophiles. They react with alkyl halides to yield ethers. So what in the world is a halohydrin? A halohydrin is an alkyl halide that has an alcohol group as a neighbor. So this, and they have to be right next door to each other. Okay, so the alcohol is 1 carbon removed from the alkyl halide. Obviously, they could also be like in this kind of pattern. This is also a halohydrin. They just have to be 1 carbon next door to each other. So what do you think is going to happen if we react these with strong bases? Alcohols react with strong bases to yield alkoxides. The hydrogen comes over to pull the proton off. The electrons that were in the bond then get localized on the O. So after the reaction occurs, you're left with an alkoxide that still has an alkyl halide on it. Let me show that reaction. Let me give myself a bond here so we can really see the bond breaking. The hydride deprotonates the alcohol. The electrons that were left get localized on the O. One, two, three, alkoxide, halide. Now, what we learned in the last slide comes into play. Alkoxides are good nucleophiles. Now we have a molecule set up that has a nucleophile and a leaving group in the same molecule. When you have that kind of bifunctionality, they can react internally. This is an intramolecular reaction happening within the same molecule. This oxygen just can kind of like slide over and be like, clink, I'm going to react here, pushing the leaving group away. The oxygen is going to react here, pushing the leaving group away. This is an intramolecular, in the same molecule, SN2 reaction, because the nucleophile comes in from 180 degrees and pushes the leaving group away in the same step. Nucleophile comes in 180 degrees, pushes the leaving group away. The product of this reaction now is an epoxide. An epoxide is a 3-membered ring, one of which is an O for them. One of the members is an O. So halohydrins, in the presence of a strong base, yield epoxides. So again, I kind of did that on the last slide. Halohydrins, in the presence of a strong base, yield an epoxide. So now let's talk about what happens when you take alcohols and you react them with acids. You already know this. So let's look at an alcohol. And again, I'll name it for you because naming alcohols is important right here. This is an alcohol. The longest chain has 4. We have a methyl group at carbon number 2 and the alcohol group at carbon number 2. This is 2-methyl, 2-butanol. There's no chiral center, so we don't have to worry about R&S configuration. We're going to react it with strong acid, hydrochloric acid. So, alcohols are amphoteric. They can either react as an acid or they can react as a base. It depends on what you put them with. They reacted as an acid, a proton donor, when you put them in the presence of strong base, sodium hydride. Here they're going to react as a base. The 2-butanol is going to react as a base in the presence of the added hydrochloric acid. Bases deprotonate acids. Acids are proton donors. So the alcohol is going to react with the acid to pull the proton off, pushing the leaving group away. You can kind of think about it that way. Really, it's an acid-base reaction, not a nucleophile-electrophile reaction. The products of the reaction look like this. And the whole point of this, when alcohols react with acids, is that it makes the alcohol group, or makes the hydroxide group, into a phenomenal leaving group. Phenomenal leaving group. Water. So now, what's going to happen here? We have a fantastic leaving group, and it just so happens to be tertiary. Tertiary groups cannot undergo the SN2 reaction. They can only undergo the SN1 reaction. So, this leaving group is simply going to leave. The product of that then is the carbocation. So now we're going to get into what can carbocations do. Multiple things. But one thing a carbocation can do when there's no added heat is react with a nucleophile. The product of that reaction then here is the chloride. So alcohols react with acids to make hydroxide groups into great leaving groups. I'll pick up in the next video on reactions of carbocations.